So far, when we've talked about acceleration, we've talked about all the acceleration happening in the same direction as the velocity. So for instance, rocks being thrown in the air, stuff falling straight down. But this isn't always the case. A lot of times, the acceleration is in different directions than the velocity. For instance, if a baseball is thrown, the baseball is thrown up, but it's also thrown over. So it has an x component to velocity and a y component to velocity. But the thing is, the gravity is only in the y component. So how do you figure this out? You have a lot of things going on at once, and it can seem a little confusing. So we go through this equation at a time. The horizontal velocity has no acceleration. It's just a velocity. So our equation for that is position equals velocity times time. Now we don't know the time yet. So we've got to go back, we've got to look at the other equation. The other equation says vertical position equals original vertical position plus v naught t plus 1/2 a t squared. That's the same thing we've talked about. Or we can say that the velocity in the y direction, v sub y squared, equals v sub y naught squared, the original y velocity, plus 2a y. So either of these equations work. So what we have to do is we have to put this together somehow. And we do this step by step at a time and very careful. So let's take another example. The baseball's thrown. We know it's the x and y components of its velocity. How far does it go? So we'll call this v sub x, the velocity in the x direction, and v sub y, the velocity in the y direction. So how far does it go? Well, first of all, let's figure out how long it stays in the air. For this, we can use a very simple equation. We know its velocity at the base here is v sub y. We know its velocity at the top is 0. So we know that's how long it takes to get to the top. And we know that velocity equals acceleration times time. And more specifically, that's change in velocity. So change in velocity is v final minus v initial equals acceleration times time. V final is just 0, so we call it negative v initial, and we'll call the acceleration gravity. So time equals negative v initial divided by gravity. So that's simple enough. Now we got to plug this back into the horizontal position. We know the horizontal position equals v sub x times t. But wait a second. This time we calculated over here, that's just the time to go up to the peak. It takes that long again to fall back down. So we've got to double that. So the time to the peak equals that, but the total time equals twice that. So the x position is going to end up being x equals v sub x times negative 2 v sub y over g. So let's write this out on a new page to be a little clearer. And let's see what this says for a second. It says if gravity's high, if we're throwing things on Jupiter or something, it's not going to go very far. That makes sense. And it says that if we have a high x velocity, it'll go farther. And if we have a high y velocity, it'll go farther. Both of which are true. If they're both higher, it'll go even farther. But what's this negative sign do? Is that a sign we did something wrong? Well, let's look. Gravity is an acceleration downward. So gravity represents a negative acceleration. So even though we write this just as a constant, really, it's a negative constant. And a negative constant divided by a negative constant is positive. So that means it should have traveled a positive distance, assuming the x velocity was positive. Now we assume the y velocity is positive, because if it's not, it'll hit the ground right away, so this problem doesn't make any sense. But as long as the x velocity is positive, it's positive. And if the x velocity is negative, it's negative. And there's a bunch of other ways we could have done this. We could have used the y naught equation, y equals y naught. Calculate time that way also. That would have given us the same value. Because we would have said that y initial, and y final are both 0. So we would have said negative v naught t equals 1/2 a t squared. So now that we have this equation, we can actually go through and start solving for stuff. Divide both sides by t. In this case, it just cancels out the t squared. In this case, it actually cancels out the t. So our new equation is negative v naught equals 1/2 a t. Multiply by 2, divide by a. Negative 2 v naught over a equals t. Now what's v naught? In this case, because we're dealing with the y direction, that'd be v sub y. So negative 2 v sub y over a equals t. The exact same thing we derived the other way. So as you can see, no matter which equation you use, You always get the same result as long as you do it right. And the trick to doing an equation is you want to use an equation that has all the variables you need, but none of the variables you don't need. So in this case, we need to incorporate acceleration, and we need to know time. And as a result, the v squared equation would not have been appropriate. It would have made things easier because we don't have to deal with time, but we wanted to know what time is. That was our goal, so we could figure out how far it traveled. So as a result, we rejected this one and picked one of our other equations. So when you're doing this kind of problem, you want to look at the equations you have, pick one that has all the variables you need, go through, plug in what variables you have, and solve for the ones you don't. And if you use this trick, you should be able to solve almost any equation of this problem of this type. But if you don't quite get it, don't worry. I'm going to do some more examples of different kinds of problems so you can see.